All right, let's do some examples and practice with determining the amount of entropy for different examples. First part, it says, for each of the following pairs, choose the substance with a higher entropy per mole at a given temperature. So the first one says solid carbon dioxide and gaseous carbon dioxide. Well, a gaseous carbon dioxide sample is going to have more, the molecules will be more spread out. We also mentioned earlier that solid has the lowest amount of entropy, then liquid, and then gas has the greatest amount. So especially if it's the same substance, we definitely know that gaseous carbon dioxide will have a greater entropy. And maybe we'll just highlight these, save on. So yes, gaseous carbon dioxide is going to be the one with the greater amount of entropy. N2 gas at 1 atmosphere and N2 gas at 0.01 atmospheres. Well, now we're looking at pressure. So greater pressure, that's compressed down in a really small space where the molecules can't move as much. But if it's lower pressure, those molecules can move around more freely and more randomly. So we would select this, and you may put a justification down here. Lower pressures allow molecules to spread out and interact more randomly. But one of the biggest things is that they are able to spread out. That's very significant to get that. All right, predict the sign of the entropy change, delta S, for each of the following processes. So we're talking about a process and deciding whether the entropy is increasing or decreasing. If the entropy increases, that's a positive delta S. If it decreases, that's a negative delta S. So we need to think about what's more random of the two. So solid sugar is added to water to form a solution. So is solid sugar or the solution going to have more randomness? Well, we learned that if something dissolves, it tends to become more random. I went from something that was solid sugar, to a solution of sugar water. That's definitely an increase in randomness. So this would be a positive delta S. And I'm just going to copy and paste delta S right here. Delta S is positive because a solution has a greater entropy or randomness than a solid. All right, iodine vapor condenses on a cold surface to form crystals. So that actually, technically speaking, it would be better to say not condense, but deposits, because that's actually a process of deposition if we're going straight from vapor to crystals. But anyway, even if it was just condensation, we're changing from a very random state of matter, which is a gas, down to either a liquid or a solid, going all the way to the solid. That's a very, very big decrease in entropy. So delta S in this case is negative. A solid has a lower amount of entropy than a vapor, right? So that means we have a decrease in the amount of randomness or in the entropy. Which of the following has the largest increase in entropy? So looking at these, which one has the largest increase in entropy? Well, the first one, I see a solid going to a gas. That's an increase in entropy, so this is definitely a possibility. Let's look at the next one. I have one gas, I've got two gases, and then over here I have, okay, two gases. So I have 2 moles of gas on the reactant side, 2 moles of gas on the product side. Is it possibly an increase in entropy? Possibly. Very well may be. But is it a big one? Is it a big change in entropy? Well, I have the same number of moles of gas on both sides, so that's not as big of a change in entropy as this first one going from a solid to a gas. All right, over here I have KNO3 as a solid becoming KNO3 as a liquid. That's a state of matter change. That's pretty substantial. But again, that's going from solid to liquid. This was going from solid to gas. It's a pretty big change. And then I have carbon as a diamond turning into carbon as graphite. There is an increase in randomness, but it's still the same state of matter. So the best choice for this, just qualitatively looking at it, would be the first one, going from a solid to a gas. All right, calculation using the standard entropy table. So sometimes you're going to have to look at a table of entropy values and then use that. You can find a table in textbooks. We'll give you a table on any assessments in AP Chemistry, and the AP Chemistry exam College Board will give you the values that you need, either in table form or embedded in the question. Delta S calculations, the way we're going to do that, the units for S are often joules per mole Kelvin. It could be joules times inverse moles times inverse Kelvin. These are equivalent. That's usually the units that are used for entropy, although it could be given in kilojoules per mole Kelvin. This is normally what you see for entropy. How do we calculate it? We've got our equation down here. Delta S standard equals the delta S of products minus delta S of reactants, or the enthalpy of products minus the enthalpy of reactants. And it's the summation. I said delta, I meant sigma. The summation of the enthalpies, the standard enthalpies of the products minus the summation of the standard enthalpies of the reactants. Products minus reactants. This is just like the main way that we learned to calculate the enthalpy of a process. Same thing. And by the way, this is given on the AP exam. This formula will be given to you. So calculate the entropy of change at 25 degrees Celsius in joules per mole Kelvin for this process. Well, how are we going to do that? We're going to look at our table, which I've got an abbreviated table down here, and we're going to calculate it. So I have 2 SO3 on the product side, and on the reactant side I have 2 SO2 and O2. Now you always want to make sure that you've got the right states of matter, so we'll try to pay attention to that. So I'm going to start by putting 2 times whatever the value is for SO3 gas. Now that's all that was given here, but in a table you might see it for solid, liquid, and gas. Pay attention to the state of matter. So 2 times 256.6, that's all of my products. Then I'm going to do minus, I have 2 SO2, so I'm going to have 2 times SO2 gas is 248.1. Plus the other reactant is oxygen, which is 205.3. And then we could just put that in a calculator and solve it. Of course, we'll be giving you easy numbers to work with. If it was on the multiple choice section, and you would have to do the math in your head. For this one, I get 2 times 256.6 minus 2 times 248.1 plus 205.3, and I am keeping that last factor all in parentheses. I'm keeping this in parentheses so that I won't make a mistake. End up with a negative 188.3 joules per mole per Kelvin. So this is how you would calculate the delta S if you were given the entropy values, the entropies of formation. So keep in mind that's what this has to do with is the entropy, standard entropies, I should say. Very similar in the way that we would calculate the enthalpy if we were trying to use enthalpies of formation to solve it. But we just use this equation in terms of entropy values that are given either like they are here or whether it's in a table. Okay, you should be able to answer any questions that you have about entropy. Work through the College Board assignment. Let me know if you have any questions.